This is a talk for many audiences. I'd like to welcome the university people, the scientists and technologists in artificial intelligence and computer science, industrial computer technologists and their business colleagues, and finally, government technologists, planners, and program managers. As I was attending the American Association of Artificial Intelligence conference in Washington recently, a bellman was bringing my bags up to my room. And he said, "What are you doing here?" I said, "Well, attending a conference." "Conference? What conference?" "Artificial intelligence." "Artificial intelligence," he said. "I thought that had already been done." The good news is we've already done a great deal. And the extra good news is we've still got lots to do. Let me tell you a story about 1981. 1981 was a fascinating time for knowledge systems. The era of commercialization of the technology was just beginning. No one knew what it would be like. Two small companies had already been started, IntelliGenetics and Technology, and soon to follow were many other small companies. I was giving a talk at the e.g.configuration conference in 1981. It was the AAAI, American Association of Artificial Intelligence presidential address. And what I chose to do in the presidential address was to look back over the era of academic research in expert systems, try to gather together the lessons of what we had learned, and project them into features and trends of the technology as it would shape up in the 1980s and 90s. I'd like to talk now about that, about knowledge systems from birth to adulthood. The mother of the technology was the science of artificial intelligence, particularly the work that AI scientists had been doing for a decade on heuristic search, problem-solving methods, and knowledge representation. The father of the technology was chemistry. That is, the Dendral project at Stanford, if you believe in the Stanford theory of history, or mathematics, the Maxima project at MIT, if you believe in the MIT theory of history. In either case, the big idea was the power of domain-specific knowledge to create high-quality problem-solving, to allow programs to behave with high quality in complex problem-solving tasks. That idea was called the knowledge is power hypothesis, and more recently has been called the knowledge principle. In the period from 1965 through 1979, these ideas were tried on a wide variety of real problems, application-oriented problems from medicine and medical diagnosis and therapy, X-ray crystallography, molecular biology, engineering, tax law, several other disciplines. By 1982, the stage was set for a broad commercialization in which the real world was going to test the technology. This led to an AI boom in the industrial and commercial sectors. The R&D groups of many companies became early adopters, later to be followed by applications groups and management information systems groups. DARPA in the government supported further work in knowledge-based systems technology through its strategic computing initiative, and the United Kingdom and the European community also launched major projects in the area. So where are we now in 1993? In 1993, several thousand knowledge-based system applications have been deployed worldwide. What we find is a remarkable diversity in the end-user task that is performed by these systems. Large payoffs of many types are described. However, the growth of the business of knowledge-based systems is slow or even negative. The computer industry, the media that covers the industry, and the users are skeptical of the technology. I'd like to begin by giving you a roadmap of this talk. Part one of my talk is is what I call the tiger part of my talk. This technology is a tiger. Knowledge systems technology is powerful, and it fits with important economic and organizational goals. The documented benefits from most deployed systems are large, in fact, sometimes remarkable. The second part of my talk is what I call the cage part of the talk. Where is the growth? Where is the demand to match the observed payoff? Why is the tiger in a cage? What are the bars of the cage? And finally, I'm going to conclude the talk with a call to action, uncaging the tiger. What can companies do to remove the bars of the cage? What can AI researchers do? And what can the government do? Let me mention how I chose these success stories. First, I've chosen significant applications from excellent work being done by parts of the United States government. Secondly, I've chosen work from emerging areas of knowledge-based system applications. And third, I've chosen to survey an old area of knowledge systems work that has had a dramatic second coming, and that is the area of configuration technology. Let me begin part one of the talk by discussing various efforts at NASA and DARPA. These are government-initiated success stories. It's a tough journey for a technology to become space qualified. Yet, recently, the first expert system has flown on a space shuttle. This is the expert system called SHOOT, stands for Superfluid Helium On-Orbit Transfer. This expert system assists astronauts in setting up, running, and diagnosing the transfer of helium in space between doers. This was a very successful application, and it was strongly accepted by the astronauts. More important is a major NASA application for assisting with ground processing applications. This is the so-called GPSS application. It's the most celebrated of NASA applications. And the people who did this application have just won the largest cash award ever made in NASA's system for rewarding meritorious technical contributions under the Space Act. GPSS schedules Kennedy Space Center operations for the recycling of the space shuttle from one flight to the next. After it comes in, before it goes vertical for the next flight, there are 5,000 to 10,000 operations that need to be performed. GPSS tracks these operations, deconflicts them, and optimizes the schedule for the ground processing. The planners interact with GPSS. GPSS is set up in the mode so that it can handle interruptible rescheduling. Obviously, in doing the thousands of operations needed to recycle the space shuttle, things do not flow smoothly, so that rescheduling is constantly necessary. In order to do this work, here I'm going to use AI jargon for a minute. The program uses constraint-based reasoning using heuristic iterative improvement search. That is, not a backtracking algorithm. What are the benefits from GPSS? One of the first benefits seen was order of magnitude gains in the speed of conducting the scheduling and the accuracy of doing the scheduling. Previously, no tasks were scheduled beyond the next day. Now, schedules are reasonably accurate out to a horizon of 11 days. Previously, schedules 2 days out were about 5% accurate. Now, schedules 2 days out are 95% accurate. GPSS saves NASA $0.5 to $1 million per flight, mostly in fewer scheduling meetings and in particular less power on time during weekends, which means less overtime cost on the weekends. The system was expensive. It cost $1.5 to $2 million and took 3 years to build. But still, at a return of half to $1 million a year, it has a very large return, a half to $1 million per flight. It has a very large return on investment. Now I'd like to switch to another success story in connection with DARPA, the Advanced Research Projects Agency of the Department of Defense, now called ARPA. ARPA has been the main supporter of AI research since 1965. ARPA was supporting a program of planning research in AI when the Desert War broke out. The ARPA program manager, Dr. Steve Cross, contacted the contractors of the planning research program and asked them if they would do a crash effort to produce a planning program as a modification of an existing manufacturing scheduling program for use in logistics planning in the Desert War. The point was to use a program to help schedule the movement of soldiers and materiel from the United States and Germany to Saudi Arabia, assisting human officers in planning what to send and how to send it. The program was called DART. DART used constraint propagation and constraint maintenance techniques. For those of you who are AI scientists and technologists, it also used a blackboard-type architecture with a relational database as the blackboard. DART offered to the planners a major gain in speed of planning. DART was used in a what-if planning mode, and what-if replanning was reduced from normally weeks to hours. DART enabled these planners to discover logistics bottlenecks in time for planners to deal effectively with the situation. For example, DART assisted people to discover an overload at a port in Europe, which allowed the DoD to open a second port. After the Desert War was over, the director of DARPA, Victor Reese, came to Stanford to give a talk. And in that talk, he pointed with pride to the DART application and mentioned that this one application paid back DARPA's entire investment in artificial intelligence research over the years, that is, since 1965. Payback in money, payback in effectiveness in helping the war effort, well, he didn't say. But he did tell the DART story proudly to Congress in his testimony at the opening of his annual budget session with Congress that year. I want to summarize some key observations from the NASA and DARPA applications. Fast is beautiful. The first thing to notice is that these applications give major speed up to thinking work. And this speed up is observed to be almost always a factor of 10, sometimes a factor of 100, or even more. The gain in speed can be a crucial success factor, for example, as it was in the DART logistics planning application. Now, why is speed up so surprising? Isn't that the purpose of computers, to speed up our work? What's interesting is that speed up was not one of the things that was expected when I projected the features of the knowledge systems technology as they might emerge in the 1980s. We know that computers are very good at speeding up calculation work, but we didn't do the appropriate extrapolation to project that they would be very successful in speeding up the work of reasoning, thinking. The second point I want to mention is that experience and knowledge of artificial intelligence enable success in the field. NASA has one of the strongest collections of artificial intelligence research scientists and technologists. Their NASA Ames Research Lab is one of the best research laboratories in artificial intelligence in the country, and they have strength at almost all the other NASA centers. DARPA, of course, is very strong in artificial intelligence. I mentioned that the program manager, Steve Cross, for the DART project. Steve is a PhD in artificial intelligence, and of course Steve's contractors are highly skilled in the art of artificial intelligence. Another lesson is that accuracy is beautiful also. Knowledge systems often increase the accuracy and lower the error rate for people doing a job assisted by the knowledge system. Sometimes accuracy is the crucial success factor. I'll discuss later the impact of accuracy on configuration. Let me mention simply in the financial systems area, the famous system of American Express called the Authorizer's Assistant increases the accuracy of making decisions about allowing customers to charge or not charge on their American Express card. The intent is to reduce the amount of bad debt and fraud that American Express experiences. Because of the increased accuracy of making those decisions, in the first year that the Authorizer's Assistant was deployed, American Express saved $55 million. The final point I want to make is that constraint-based reasoning methods have a broad applicability. We saw them apply to scheduling and planning, and later we'll see them applied to configuration. Let me pause for just a moment to address a question that may be on the minds of many of the people viewing this lecture who may not have had much contact with the artificial intelligence technology. How are the knowledge system applications different from conventional applications, which are also faster and more accurate than people? Conventional programs represent their various domains as numbers and as algebraic formulas. Knowledge systems use wide-ranging symbolic representations of the knowledge in their various worlds. Of the numbers and formulas are just special cases of symbolic representations. Conventional programs use the operations add, subtract, multiply, and divide, whereas knowledge systems use operations of symbolic logic, augmented by probabilistic logic, to derive lines of reasoning leading to the solution of problems. In short, conventional programs calculate their way to an answer, and knowledge systems reason their way to an answer. Let me switch now to the second part of my tiger tale, to discuss compliance with laws, rules, and regulations. The problem of compliance is one of complexity. These laws, rules, and regulations by which we live and work are too complex often for us to think our way through. Let me illustrate the use of knowledge systems in assisting people in these tasks by discussing two systems that are used for handling welfare decision-making: the Tulare Touch system, otherwise known as Caine, and the Merced County system, known as MAGIC. From the citizen's point of view, the problem is that he or she wants a rapid response to a request for welfare. The government's problem is that although it wants to be generous, it also wants not to pay ineligibles. And furthermore, the caseload for the government is increasing. Tulare County, working with Macro Systems and IBM and other contractors, developed a system called Caine, Client Entry Assistance Network. This expert system determines the eligibility of citizens for aid to dependent children, food stamps, and Medicaid, and if eligible, how much. 85% of the applicants for welfare use the touch system. They enter their relevant data at a kiosk equipped with touch-sensitive screens, hence the name of the system, Tulare Touch. This system is a rule-based system. It uses several knowledge bases. Approximately 3,000 to 4,000 rules determine the aid for dependent children. 2,000 rules govern the eligibility for food stamps, and about 5,000 rules for Medicaid. In other words, these are fairly significant knowledge bases. What's the benefit to the applicant? The average time to determine eligibility has decreased from 25 days to 6 days. Now, the 6 days, of course, has nothing to do with the expert system, which can make the determination in seconds. In these 6 days, various legal things, like, for example, looking up a person's driving record and so on, are handled. The government itself reduced the caseworker load in handling these by 25%. And furthermore, the error rate in determining eligibility has dropped dramatically. For unassisted operation, that error rate is typically 3 to 5%, but it's less than 1% when assisted by Caine. Caine is now being prototyped for an application in Oklahoma, and it's hoped that each state will adopt this system over time. A similar system was done by Merced County, California, in connection with Anderson Consulting. This system aids the social worker at the time of the applicant interview. The person is still interviewing the citizen, but now the aid worker has the expert system as an assist. Since August of 1990, the caseload has gone up 63% in Merced County, but the staff requirement to handle this increased caseload has decreased by 9%. The training time to train a fully qualified social worker has dropped from 6 to 9 months down to 13 half-day sessions. This training effect alone saves millions of dollars per year. Now let me make some observations about compliance advisors, which I also call rule helpers, helping us with complex rule systems. This is a very important class of applications of expert systems. It's a class of expert systems that diffuses well into large bodies of people, because all of us have to comply with rules and regulations and laws. Knowledge systems usually are dedicated to small user groups. That is, expert systems are specialized systems, hence have small user groups. But rule helping systems, compliance advisors, typically have large bodies of people that they are assisting. These are the simplest knowledge systems to implement, least expensive. The knowledge acquisition is quite simple because the rules and the regulations and the laws are laid out in black and white in some procedure manual or some legal document. The inference engine is usually very simple, and the space of applications for these rule helpers appears to be endless. In sketching the tiger in the tiger part of my talk, I've covered two classes of systems already: planning and scheduling systems, as in GPSS and DART, and the compliance advisors, the Tulare Touch system and the Merced Magic system. I now want to describe an important new field called knowledge publishing. And finally, I'll conclude this sketch of the tiger with a discussion of configuration applications. Let me talk about active books for a moment. The normal book that we use to assist us is a passive object. It's a dead object. It sits on the shelf or it sits on our desk, awaiting us to open it, to apply our intelligence, to read it, to extract the knowledge that is relevant to the problem at hand, the problem in context. That book does nothing for us. It's a passive entity. The expert systems or knowledge systems called knowledge publishing systems, on the other hand, deliver knowledge to the user specifically in the context of a user need or request. It's a live object. It's an active object, not a dead object. The goal of knowledge publishing is to disseminate knowledge in forms other than on paper. A good example of a system in knowledge publishing is a well-known tax advisor called Andrew Tobias's Tax Cut. It was developed by Dan Caine and his wife Claire Caine. Dan is a tax attorney in Boston, and Claire Caine is a knowledge engineer in the Boston area. It was originally called Ask Dan About Your Taxes. Later it was sold to the Andrew Tobias company to be incorporated with Andrew Tobias's income tax filling out forms in a program called Tax Cut. It's a rule-based knowledge system that has about 1,000 rules and employs backward chaining. Dan Caine and 3 tax lawyers that he employs do maintenance on the knowledge base and keep it up to date. In the last tax season alone, Tax Cut sold 250,000 copies. A similar example is a program called Grammatik. Grammatik does for you what your English teacher used to do for you. It checks your grammar. We know all about spelling checkers. Grammatik is an expert system to check grammar, not spelling. Grammatik has sold more than 1 million copies now in several languages. Finally, let me mention the expert system distributed by the computer company Compaq with printers that are sold by Compaq. The program is called QuickSource, and it was described in a paper at the 1993 Innovative Applications of Artificial Intelligence conference. QuickSource assists Compaq users in solving complex networked printer problems. The benefit for Compaq is that it reduces the load on Compaq's helpline, the 800 number where users get help, and that saves Compaq a lot of money. But most important, say the Compaq people, is the effect that enables Compaq to differentiate its product from other products on the market in terms of advanced technology that's being used, service to the customer. QuickSource is a rule-based reasoning program combined with a case-based reasoning program. It uses software from Inference Corporation called CasePoint, and approximately 500 cases are used to assist the user. In addition, the system is delivered with its manual type information, including the graphics, online, so that the user doesn't even have to deal with paper in connection with the manual. Compaq has done an extensive benefits analysis and showed that users are now solving about 20% of their complex network printer problems by themselves. That is, conservatively speaking, there are about 20% fewer calls to the Compaq hotline. This alone translates into savings to Compaq of $10 million to $20 million per year just in the customer service operations. But there are other benefits in product differentiation, customer satisfaction. These were all evaluated as significant, in fact, some as essentially strategic, even though they were not quantified by Compaq. I want to review the points concerning knowledge publishing. Knowledge publishing, I believe, will be an important new industry. The knowledge publishing effort is introducing new products into the economy as a result of knowledge systems technology, and indeed, in my view, will probably become the largest field for future knowledge system applications. The first wave of knowledge publishing active books is already here. We are in it now, and these systems are easy to implement because they consist of rules, regulations, laws, and forms. The second wave of knowledge publishing systems will be much more difficult because that would rely on the representation of complex models of the world. As PCs become almost universal in people's homes and businesses, Companies will prefer to distribute their procedure manuals in this active form rather than in the traditional but unread paper. Companies are getting the idea that users simply will not enter the large bodies of manual paper that sits on their shelves to get advice. They'll call the hotline or they'll get angry themselves and frustrated with the software. So businesses are moving in the direction of putting their procedure manuals into this active book form. I want to move to the last part of my tiger tales, and this is the tales of configuration, revisiting the configuration task. I'm going to talk about configuration tasks for computers, for homes, and for selling anything complex. Mass customization is an idea whose age is dawning. A century ago, we saw the dawning of mass production of regular products. Now, with the advent of complex information processing, we are enabling mass customization. Tell me what you want, and we'll make that for you. Configuration is a task which is central to mass customization, and it is a task that is well known and much beloved by artificial intelligence science and technologists. Configuration problems themselves are ubiquitous because in modern life, most engineered and manufactured products are made from subassemblies, which have to be configured into a larger product. As we move towards semi-custom ordering, semi-custom design, manufacturing, we will place great knowledge demands, and we will be facing great combinatorial complexity. Both of those problems can be assisted by the use of knowledge systems. The first industrial application of a knowledge system was a configuration application. That was the famous XCON system done by Digital Equipment Corporation for configuring mini-computers, particularly their line of VAX computers. XCON was followed by a sales helper, a sales expert system called Excel, which enabled a salesperson to configure the mini-computer at selling time rather than the system engineer configuring the computer at manufacturing time. XCON and Excel were enormously successful. DEC reports savings over the years of hundreds of millions of dollars. Because of this great success, configuration applications were done by IBM for its line of mini-computers, Unisys, ICL, and other computer manufacturers. But it turned out that configuration applications are more general than just computer applications. Let me talk about applications to the construction of factory-built modular homes. Sekisui Heim is a Japanese modular home builder, the fourth largest in Japan. Sekisui is a plastics company. Sekisui Heim is a subsidiary or division that builds factory-built homes, 25,000 of them each year. In the Sekisui application, the customer designs her own home with the help of a salesperson on a portable computer, and the architectural specifications for that home are sent to the factory after the customer order is signed. To build that home will require the use of about 5,000 parts out of an inventory of 300,000 different parts that Sekisui Heim has. But which 5,000 parts should be picked for this particular customer's home? The Sekisui configuration program works out the particular parts picking plan for the specific home that the customer has designed, and thereby enables the flow of parts from the inventory to the factory floor for assembly. That task requires not only very detailed product models of these different lines of homes that Sekisui sells, but also constraint-based reasoning. The Sekisui configuration program reduces the errors made in parts picking. The steady state value for those errors made by highly trained people, steady state value is about 5%. And in the steady state, the configuration program reduces that to 0. It also reduces to 0 the errors made during the learning curve when a new line of homes is introduced by the architectural design center to the factory. During that period, the first 6 months, the error rate can be as high as 30%, and the use of the program, again, reduces that to 0. In reducing these errors, the configuration program saves Sekisui Heim about 1 billion yen per year. At current exchange rates, that's about $9 million per year. To write the system was expensive, but there's such a big return on investment. The payback in this case is 6 months. 6 months of running the system paid back the entire cost of building the system. The broadest attack on the mass customization problem is Trilogy Development Group's Sales Builder program. Trilogy sells knowledge systems that make the build-to-order concept both possible and efficient. Trilogy sells the inference engines, that is the process programs to do the reasoning, and they also do the knowledge bases for the companies on contract. The techniques used are familiar techniques to AI technologists. They're constraint-based reasoning techniques using an object-oriented framework for defining the products, for building the product models. Sales builder applications have been done, for example, for AT&T to configure complex PBS systems. In the AT&T application, the configuration time was reduced from days to minutes. Imagine what that means to a customer and to a salesperson in a sales situation, especially if your competition doesn't have that ability. Other applications that Trilogy has done include configuration of PCs for Dell, IBM, Digital, NEC, configuring medical equipment for GE, configuring local area networks, and many more configuring applications. At the present time, Trilogy is launching a knowledge service. That is, a service in which the customer will be able to access a program called Conquer. Conquer stands for Configuration, Quote, and Ordering, in order to order a PC, get a price quote, and then place the order. The payoff of all of this is that last year, says the Trilogy management, Trilogy was the fastest growing software company in the United States as measured in percentage growth in revenues. That's interesting because this is the AI technology. This is an innovative application of artificial intelligence. This is central to what the AI people, the expert systems people know how to do, and it has yielded a company of very rapid growth in the software industry. What can we say about configuration tasks? Configuration tasks are surprisingly omnipresent in the world of work and surprisingly important. Many problems that you wouldn't expect fit the configuration task model. To enable the concept of mass customization, a concept which is coming, the configuration technology is crucial. Constraint-based methods of the kind that we know very well in AI are central to conducting these configuration tasks. And finally, they have very large payoff, an example being the Sekisui Heim application, very large return on investment. Now I'd like to summarize what I've said about the tiger. We have here a genuine tiger, not a paper tiger. 10,000 operational knowledge systems have been deployed worldwide, roughly speaking. And there are millions of knowledge systems deployed if you count TaxCut, Grammatique, and other of the knowledge publishing products. These applications show important broad benefits. The first is transfer of expertise from expert to technician and across the organization. The second is speed up, order of magnitude speed up of human problem solving and decision making when assisted by a knowledge system. The third is quality improvement, significant reduction in error rate when a knowledge system assists a person. Improved quality has large economic payoffs. The fourth is impressive return on investment percentages and cost saving, which are seen to be at the outer edge of those that are normal for a new technology. The fifth is the creation of many new knowledge products and services and a major new way to deliver knowledge. And last, we've seen the use of the technology to empower people to deal with complex rules, regulations, procedures, forms, instructions, and so on. Now I'd like to move to the cage section of my talk. I'd like to discuss the cage and the kinds of bars that we see that are holding the tiger in the cage. In beginning this section on the cage, I'd like to give my thanks to two people who have helped me with ideas and discussions, Avrin Bar and Herbert Shore. What kind of growth might we have expected for knowledge systems? That is, when we say that knowledge systems has not achieved exponential growth, what do we mean? Let me give you, for example, the figures for the growth of the relational database company Oracle as an example of companies in that industry. The relational database technology was invented in the early 1970s. Companies were formed in the late 1970s and early 1980s. Oracle's revenues in 1983 were $5 million. In 1986, their revenue was $55 million. In 1989, $584 million. In other words, a factor of 10 every 3 years. In 1991, those revenues passed $1 billion, and in 1993, $1.5 billion per year. And that doesn't include the revenues of other relational database companies like Ingres, Informix, Sybase. That's the kind of growth we might have expected. And that's the kind of growth that we haven't seen, even though we've seen steady linear progress. Why? There are three things that are important in the development of a knowledge-based system: knowledge, knowledge, and knowledge. One of the speakers at the recent Innovative Applications of Artificial Intelligence conference quoted from the American Heritage Dictionary the definition of the term intelligence. Intelligence is the capturing and use of knowledge. Our field forgot its battle plan. The battle plan was the knowledge principle, the knowledge is power hypothesis. Reminds me of the movie Shadow Warrior by Kurosawa. In that movie, the battle plan of the Takeda clan was, the mountain shall not move. But then Takeda Shingen dies, and the people who follow him violate that plan. They take the army down the mountain, and the army is massacred, and so is the Takeda clan. The mountain moved. The battle was lost. Our field forgot its battle plan. The battle plan said that of primary importance in making programs intelligent was the knowledge that they have about their domain of discourse, and only of secondary importance is the problem-solving method employed. Yet most companies sold knowledge-free shells. They sold shells called advanced reasoning tool or knowledge engineering environment, as opposed to selling shells like steel mill scheduling program or manufacturing planning program. They sold reasoning, not answers. One of the most spectacular cases of this kind of development was in Japan in the 5th generation project. A tremendous national effort was invested in constructing an excellent machine that handled 150 million logical inference steps per second. But that project developed very few knowledge bases to put those 150 million inference steps per second to work on any killer application in the society. Closely related is the second bar of the cage, knowledge acquisition. Back in the days when I was surveying the field and projecting where it was going to go, I called knowledge acquisition the knowledge systems bottleneck. And in the 1980s, that bottleneck was not broken. To use the words of Mr. Sato, the director of Fujitsu Laboratories, in describing the work of his company in the area, the trouble that they've been having, it has been too difficult to get the knowledge. He remembered the knowledge principle. Knowledge acquisition is hard because we are trying to capture a significant chunk of a complex, messy world. We haven't had enough knowledge acquisition tools, and that's probably because we haven't had enough ideas about knowledge acquisition to construct those tools. Our ideas have been too weak. We've attempted to construct task-oriented tools, for example, tools oriented toward diagnosis. But these have not had a big impact, and they have not yet been good enough. The third bar on the cage is the knowledge system's narrow niche. If the domain of applicability is too broad, then by the knowledge principle, the system lacks power. If the system is appropriately narrow, then the user group might be too small. Narrow implies specialization. In a specialty, the problem solving is powerful, but the user group is small. But a large user group is needed to amortize the large costs associated with knowledge acquisition. We notice in our technology that there is no knowledge reuse outside of the narrow niche. In database systems, that's not true. Data is often subject to intense reuse for many different purposes. But in knowledge systems technology, almost never is knowledge reused, and knowledge acquisition is expensive, so that's a very inefficient process. And finally, we have a narrow niche in another sense. Knowledge systems must do a wide range of tasks for the user in order to win a place in the user's world. Mathematica, for example, has won a place in a lot of users' worlds because it handles a very wide variety of tasks in symbolic manipulation of mathematical expressions. Programs that we developed at Stanford, Dendral program in chemistry and the Mycin program in infectious disease diagnosis, did not win a place among the users because it handled problems which were too narrow. The niche was too narrow. We didn't make our programs, our development tools, easy enough for users to use. We gave users complex, quirky, slow-acting software. The average user of our knowledge system software is not a rocket scientist. Indeed, not even a brain surgeon. We had a misleading experience in the first few years of knowledge systems technology because we were dealing with the R&D people of large companies. These people are indeed rocket scientists. And we got the impression that all of our users would be of that type of user. We ignored the simple motto, keep it simple, stupid. We gave users jet plane cockpits and 30 megabyte memory images costing thousands of dollars. But surprise, what the user really wanted was low cost, high speed, and a reasonable size of memory for the program. We defined our goal as being the expert system goal, the goal of achieving world-class problem-solving behavior. We could have picked simpler systems. What we forgot were the simpler rule systems, the forms, the procedures, the government regulations, and so on. The maintenance problem. Recall the knowledge principle. It says that programs are capable of high-quality problem solving to the extent that they have very good knowledge about their domain of discourse, their world. But knowledge changes over time. So the power of a knowledge-based system decays over time unless there is significant maintenance and update done to the knowledge bases. These knowledge bases must be routinely updated. In planning for organizational use of the expert system, the champions of the expert system in the companies and also the champions of the technology forgot about the maintenance problem. Maintenance personnel, maintenance tools were rarely institutionalized in the process that a company uses to develop and maintain its software. The result is that there were many good systems that simply faded away over time. They were rolled out, they were successful, but because of the lack of maintenance, they faded, and eventually they just died. We did not adopt standards of our technology. In 1987, after I had finished the interviews that led to the book, The Rise of the Expert Company, that I co-authored with McCorduck and Nee, I had many stories of large benefits from the use of expert systems technology in businesses, in commerce. And I took these stories to my friend Gordon Bell and asked him to comment on these stories, particularly to comment on why, if the benefits were so great, the terminology I was using today is, if the technology was such a tiger, then why was the technology not exploding? Why was it not booming in use? And Gordon said, wisely I think, your industry is confusing and frustrating your users by not adopting standards. Why don't you compete on service, not syntax? Standards were shunned by the academics in the field, as they normally shun standards, and they were shunned by the overcompetitive small firms in the industry. And what happened? We confused the users, we confused the developers and the managers, but particularly the managers. The managers want assurance that they are buying into a standard. It could be a proprietary standard, for example, IBM operating systems or DOS or some other proprietary standard. They're very concerned about non-standard technologies. We never developed a standard methodology for testing our program. Corporations and agencies are very concerned and edgy about testing and validation. If they're going to turn important tasks over to knowledge-based systems, they want to validate the knowledge. They want to validate the problem-solving procedure. And we developed for them no standard methodology for building and testing these knowledge bases. The infrastructure barriers to the technology were daunting. My friend Avrin Bar tells a story about Edison and the light bulb. Edison worked for years developing the light bulb, and when he was finished with a working light bulb, there was not a single socket in the world to plug it into. Edison had to develop the electric generators. He had to develop the Edison Electric Company in order to provide the infrastructure necessary to make the light bulb a viable invention. The 1980s posed a decade's worth of problems for AI technologists concerning the infrastructure. I'm going to recount these not as a way of giving excuses, but just as telling some facts about the situation. The knowledge systems people required some technologies that were not standard in the world of the computing infrastructure during that period. In the early 1980s, when they were requiring workstations and significant desktop power, that did not yet exist. The early workstation companies were just getting born. Large memories on the desktop did not exist. And we were proposing 16 megabyte, 24 megabyte, 32 megabyte memory images. Graphical user interfaces. We introduced those, but they were not common in the computing world. Object-oriented programming, for example, still is not common in the world of the data processing community. rapid prototyping methodology went counter to the standard waterfall method that was used by the management information systems people. All of these technologies are now becoming part of the standard infrastructure, but they were not during the 1980s. In short, the infrastructure was not under the control of the artificial intelligence and knowledge-based systems technologists who were dealing with the technology. One could be historical and philosophical and say that for some technologies, for all technologies, time must pass. It was 25 years from the invention of the reaper to its first use in farming. It was 25 years from the invention of the telephone to the first pay telephone call. Some technologies take 25 years or more to make it. Relational databases were invented in the early 1970s, but they didn't make it till the late 1980s. Object-oriented programming was invented in 1967. That was with Simula. And it hasn't quite made it yet into the world of computing. Finally, about expectations. The expectations of business people and the media were calibrated to the idea of general intelligence, not to the more realistic idea of narrow niche problem solving. But our technology could not support a wide range of general intelligence tasks like common sense reasoning, like learning, speech understanding, natural language understanding. Even specifically in the problem-solving areas, our early methods were sometimes awkward and sometimes useless. The technology is much more powerful now than it was then, and so it's time to carefully reset the expectations of the media and the business people. Let me summarize the bars of the cage. Knowledge, 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 the primacy of knowledge. That's the most important of the bars of the cage. The second is the difficulty of the task of knowledge acquisition. The third is the narrow niche that knowledge systems occupy. The fourth is the problem of ease of use, the need for cheaper systems, faster systems, systems that use less memory. We need to develop the simple systems first. We need to institutionalize the maintenance and updating of knowledge bases. Standards are needed. We need to overcome the infrastructure barriers. And finally, we have to live with the time lag in the acceptance of a new technology and the expectations of our user communities and the media for intelligent systems. I'd like to conclude my talk now by discussing a call to action, how we can uncage the tiger. I'd like to talk about some things that companies can do, some things that AI researchers can do, and what the government can do to help. Companies have to learn how to sell knowledge-full systems that give answers, not knowledge-free systems that do reasoning. This is difficult. It was tried by many companies that did not succeed. But we have to figure out how to do this. We have to do more systems like Sales Builder, more systems like Tax Cut, systems that give answers to problems. Secondly, companies have to make their application and development software much easier to use. The role model for this is spreadsheets. The use of spreadsheets revolutionized programming. Millions of people that never thought of themselves as programmers could construct fairly complex programs. We need to focus on making the task of knowledge representation and knowledge acquisition much easier. These are the central tasks in knowledge system construction. Our companies need to get together to agree on standards to stop frustrating the users. And finally, the companies need to look more carefully at the questions of software quality. That is, making software cheaper, faster, and smaller in the sense of using less memory. What can the artificial intelligence research community do? Well, remembering that knowledge is power, we have to develop the technology and the content for large knowledge bases so that the developers of knowledge-based systems don't each time have to start from scratch. Knowledge acquisition is too hard a problem to allow for starting from scratch each time. It's too inefficient and too costly. We have to find ways to share knowledge, or buy knowledge, or download knowledge, compile knowledge. There are efforts like this underway. At MCC in Austin, Texas, the Psych knowledge base. We need more knowledge bases like Psych, but not for common sense, but for other fields like engineering, science, medicine, law, many other fields of human work. The Japanese have proposed a large national project to start next April in exactly this area, and they're going to try to focus the next generation of artificial intelligence research in that direction. We need to develop the technology for knowledge base reuse and sharing. The costs of knowledge representation and knowledge acquisition need to be shared over a large body of users. The span of problems need to be stretched. We Americans have a small national project in this direction. More research is needed on practical machine learning methods. The AI research community had an excellent decade of research in machine learning in the 1980s, but none of those machine learning methods have turned out to be practical, or at least very few of them. We don't see them in the common everyday knowledge system development and application tools. Perhaps some breakthroughs are needed to finally put an end to this bottleneck, this expensive, debilitating bottleneck called the knowledge acquisition bottleneck. What can governments do to help? One of the most important things that the governments can do is to use knowledge systems widely to improve their own efficiency, to assist compliance, to help citizens understanding rules and laws and forms, and, by the way, to solve complex problems, as, for example, in the NASA GPSS scheduling operation. When the Republic of Singapore decided to build up its computer industry more than a decade ago, it did that first by a broad-ranging government program for automating government activities, and that gave a very wide base to the technology. We need that now in the knowledge systems area, government to use knowledge systems. Secondly, government can do what it does often so well, organize and support the development of a new technology, a second generation of knowledge systems, science, and technology, including the necessary underlying artificial intelligence research to pull it off. Fortunately, there is a major national activity going on right now that can serve as the framework for this effort, and that is the national information infrastructure that is being promoted and organized by the Clinton administration, especially Vice President Gore. The national information infrastructure and its national information superhighway is certainly destined for more than just graphical pictures and video conferencing. Knowledge should be at the center of the national information infrastructure. Knowledge publishing, active books distributed on a national scale into homes and businesses and offices. Knowledge informing everything we do. In 1986, I participated in a conference at the Corporation for National Research Initiatives on the National Knowledge Base Project. At that conference was Professor Marvin Minsky of MIT, one of my colleagues, and the two of us were engaging in a kind of a thought experiment on what it would be like we were trying to envision what the knowledge systems, technology, and community would be like in the year 2030. And one way we did that was to envision ourselves standing in the library of the future in the year 2030, looking back at the 1980s. And Marvin Minsky said something very interesting at the time, very thought-provoking. He said, imagine what it was like back then when the books didn't talk to each other. When we talk about the national information infrastructure handling knowledge systems technology, we're talking about making the books talk to each other. Knowledge systems technology should and must be part of the infrastructure that we call the society of the knowledge worker. Thank you.